Morning, everybody. So last class we were discussing this online clustering algorithm, which is an online version of the k-means clustering algorithm, and it's also called competitive learning. So this is the so if you have centroids, k centroids, which are given by mi, then in this case you again minimize same cost function for a given data point. Look at the nearest centroid and move it towards it. So that's given by this equation. Now, this can be obtained by simply performing gradient descent on this sum squared error function. Okay, so then we looked at this concept of scale, right, which leads us to the idea of scale-based clustering, because that, as I said, this is another way to derive a hierarchical clustering algorithm. So, in the basic idea of scale-based clustering is done at a given scale, right? So, because in case of k-means clustering or its online version in competitive learning, you look at the nearest centroid and then move towards it. But if you want to cluster at a given scale, you need to add another constraint to this, that is, move a centroid towards yourself only if the centroid is within some radius given by some scale parameter sigma, right? So that means moving a centroid only if it is within a radius. So how do you incorporate that condition? One way is to simply apply this condition straight away. That is, if mi is the closest centroid, and if distance between x minus mi, that is norm of x minus mi, is less than some sigma, only then go ahead and execute this equation. So the same thing, this condition of distance condition, of radius condition, can be applied in a slightly more elegant fashion, in a slightly more soft fashion, not abruptly like this, by using a Gaussian function, where Gaussian function is given by so exponential minus x minus mi mod square by sigma square. Okay, so this function looks like this. It has high value, roughly speaking, high value for xi minus mi less than sigma, and it kind of drops right exponentially as this quantity increases beyond that value. So now if you want to move the centroid towards data point in such a way that this condition is also satisfied, one way to modify this equation is as follows. So delta mi is equal to eta of exponential minus x minus mi. So now if you see this equation, you are doing the update of x minus mi just like before, but this is now weighted by another function which is significantly high only when x is sufficiently close to mi. Right, when xi minus mi is norm is too big, then this becomes small. So mi is not attracted towards xi. So this is very similar to this abrupt cost function, right? Only thing is it is done in a smoother fashion, not abruptly at that inside that radius, but so if the distance is more than that radius, it punishes that in a more soft fashion. So if you update MIs like this, then you don't even have to worry about the nearest condition, that is nearest neighbor condition. Because you don't have to explicitly check if MI is the nearest centroid. You basically do this for all x and for all mi. Okay, and so do this always, right? Then that this Gaussian will take care of. So thing is here in the previous case we wanted to have a cost function where you only compare a given centroid with all the points in its cluster. That in its cluster is now taken care of by the scale parameter and is Gaussian. So you don't have to specifically look for nearest neighbor. You just run the data, run this equation, this update rule over all the data and all the centroids, and this Gaussian will take care of this nearness. because the update will really show some results only when X and MI are sufficiently close. So let us see how it works. So this kind of clustering is called scale-based clustering. Okay, and so we saw these examples before. So if you have set of data like this, if I cluster it at a small scale, it look like, right, there are 4 clusters. If we cluster it at a slightly larger scale, it looks like there are 2 clusters. So how does it work? How do you cluster data like this? So start with a large number of clusters initially. So let us say I have a data set like this. Okay, so again, it's a kind of carefully handcrafted data, so that at one scale there are 4 clusters and at another scale there are 2 clusters. So start with, so you have some data set. Now start with a large number of cluster centers, so that are centroids. So let us say you have lots of them. So although there are, I'm taking some, let's say 12 centroids. So now cluster the data using this rule, right? So this rule. Right, start with a cluster it, start with a small sigma and cluster it, and gradually increase sigma. So as sigma, so let me call this scale sigma is equal to sigma 1, and call this bigger scale sigma is equal to sigma 2. Okay, so as sigma tends to sigma 1, right, these centroids will start moving uh, towards the center of this entire data set, right, or this cluster. And right, since if you want to cluster this part of the data at a scale equal to sigma 1, there's only one such cluster, right? So what happens if you have 3 centroids? So what happens is all these 3 centroids will merge at a common point, right? And that's only representative. So although you start with 3 centroids, you only effectively have one centroid because they all coalesce and merge at one point. And this doesn't happen in K-means. In K-means, if you have separate centroids, they all remain separate. But the nice thing about scale-based clustering is if you have too many centroids, and if your data is all very close, right, and if I'm clustering it at a sufficiently large scale, and if I start with too many centroids, they all merge, right, because you are clustering it at a given scale, and at that given scale, there is only one cluster. Then even if you have too many centroids there, they all merge, and it will only give you one cluster. Okay, so the number of clusters is determined by the scale and not by the number of centroids you have initialized it with. This is what is special about scale-based clustering. So you can start with large number of centroids, but it is the scale parameter that determines how many centroids are actually remain. That means centroids start coalescing, and you won't have that many unique centroids. They start merging. So similarly, at a scale of about sigma equal to sigma 1, these fellows also start merging, come closer and start merging. So at about sigma equal to sigma 1, you will have probably, so at sigma is equal to or tending towards sigma 1, you will have approximately 4 clusters. Now increase sigma further, and let sigma tend to sigma 2. Can somebody tell me what will happen when sigma tends to sigma 2? Any responses? Hello, are people listening? Okay, at sigma equal to sigma 2, these two centroids also start merging. And then you'll have just one centroid for the entire region, because at this larger scale of sigma 2, this is the only cluster available. So similarly, at sigma equal sigma 2 on this side, these two fellows also start merging. They start coming together. You will just have one cluster. So at sigma equal sigma 2, you will have two clusters. And let me call a bigger scale of this, where sigma is equal to sigma 3. So that is, you increase sigma further, and when you sigma goes to sigma 3, right? Can somebody guess what will be the number of clusters?
One.
Sorry?
One cluster.
Yeah, one cluster, very good. Just one cluster, okay? So that is how the scale parameter determines the number of clusters you have. So same thing in this data set. So if in this data kind of handcrafted so that there are 4 clusters at small scale and 2 clusters at larger scale. So you see that for a scale of about this value, like about 0.2, if you cluster it, you'll have 4 clusters. For a scale of about 0.4 or 0.5, right, you will find 2 clusters. At a scale of about say 1.5, right, you will find that whole data set becomes one cluster. So how do you portray this? Can you portray all the clusters in a single map? Okay, that can be done provided it's a one-dimensional data. But you find some very interesting results when you portray it like this. So plot the scale parameter on the x-axis. So this is a scale parameter or sigma. And plot your centroids on the y-axis. So let us say initially I start with some, I don't know, 10, 15 centroids, let us say. I can't see, the lines are very thin. So, and then I gradually increase centroid, the scale value. So centroids also change a little bit. So they're almost flat, so they don't change much. But as the scale increases, you see that some centroids, so here I have two centroids, one is like this, another is like this. When this scale parameter reached about this value, these two centroids merge. So now there's another centroid running here. When scale reached about this value, this centroid also merge with this previous branch, right? So similarly here also you can see several mergers. So this centroid is running like this, another one has joined it, another one has joined it a bit later. So you see that although we start with lots of centroids, some 10, 15 centroids, as you increase scale, they all start merging. So when centroids merge, effectively the number of centroids is going down. So unlike k-means, where the number of centroids is given to you, and the algorithm then gives you only that many clusters, it by itself doesn't have any opinion on how many clusters are actually present in data. Whereas in k-means, it's not like that. So given the sigma value, it will tell you how many clusters are there. And for the sigma in this, roughly in this range, see this, so this range from here to here, okay, from here to here, you see that there are 4 clusters, 1, 2, 3, 4. And these are the 4 clusters that correspond to these 4 clusters at 0.5, 0.7, sort of 0.7, 1.4 and 1.7, something like that. So there are 4 clusters, you see that. So roughly you see those 4 clusters, 1.4, 1.7, and 0.5 and 0.7, something like that. Now as you increase sigma further, even these 4 clusters merge, right here, beyond this value of, I don't know, 0.1, little more than 0.1. Right, and so you have only 2 clusters. And as you go further, this is close to 1, right, because this 10 power 0, close to 1. Even those 2 clusters merge, and you have only 1 cluster beyond that point. So you can go further, you can increase scale beyond, right, and you will have only 1 cluster beyond that. So you see that the sigma controls how many clusters you have. So there are several things that comments we can make about this. First of all, it gives you a very nice hierarchical clustering, right? We didn't intend it to be hierarchical because in hierarchical clustering that we have seen before, let's say for an agglomerative clustering, you wanted to construct a hierarchical tree structure and then you start merging dots and points and all that. But here we just wanted to cluster it at various sigma levels. And when you go from a small scale to large scale, the centroids start merging and you have a tree structure. So just I want to again point out that sigma can go from small to large, but the reverse thing is not permitted because when let's just start with only the large sigma, then everything just coalesces at this point, and from that point, if you start decreasing sigma, nothing will happen, right? They won't just separate like that. Okay, unless you add noise and do some extra stuff. But when you go from small sigmas to large sigmas, and if you start with a lot of random initial centroids, they will start merging. So this can only be normally worked out in one direction, that is from small sigma to large sigma. So this process, you get hierarchical clustering, and unlike in k-means, the algorithm itself will suggest how many clusters are there. But then you might have an objection here. I mean, you might say that it's not really different from k-means because in k-means you specify k and it gives you a number of clusters. And here you are specifying sigma and it gives you a number of clusters. How is it different? And both seem to be about the same. Okay, the answer is yes, in a way it appears like that, but there is one important difference in scale-based clustering, which is when you look at the number of clusters that you have, right? For sigma less than this value, the number of clusters varies a lot. So if you look at here, the number of clusters, as you look at a small range of variation of sigma, right? You see lots of mergers, and and you'll see that the number of clusters varies a lot. But if you look at this stretch, right, you see that there are 4 prominent clusters, and a lot of other clusters have merged in them. 4 prominent clusters, and no more mergers from here to here. Similarly, from this point to this point, again there are no more mergers. And also you might have noticed that the sigma is given in log scale. Okay, and so therefore you see that over certain intervals of scale, the number of clusters remain constant or stable. Over certain other intervals of scale, let's say if I'm looking at from here to here, a lot of mergers going on within this, right? So number of clusters is not stable. So there are certain intervals of the log scale, this intervals of sigma, where the number of clusters is stable, the other interval where it's not stable. So now if you can ask the question, how many clusters are actually present in this data set? Right, this is a question that Kevin has no answer for. But at least does scale-based clustering have an answer to this question? What do you think? Any opinion on this? Anybody? Where is my friend Krishan, who always had some questions? So does scale-based clustering answer the question? How many clusters are really there in this data set? Because up to this point, it looks almost sigma. I mean, sigma is like k in k-means and doesn't look like there is any difference. Okay, the answer to that question is the number of clusters that live over the longest scale interval, right? They can be considered to be the real set of clusters present in data. So the cluster set present or that exists over the longest scale interval, these can be taken to be the real clusters in the data set. Okay, so this is a very interesting approach to the problem. So this is what is special about scale-based clustering. But the thing is, this is obviously computationally quite intensive because you have to execute it at continuously at lots of scale values, right, and construct this tree, and then look at these intervals, and see over which interval range, right, the clusters are stable. And also, we have done this for a one-dimensional data. By imagine doing same thing in n dimensions, right? Especially the dimensions is high. Constructing this whole tree is very computationally expensive particularly because of this Gaussian computation. And you have this factor showing up everywhere, right? And that's computationally quite expensive. There's a lot of applications of this in image processing, where you look for certain regions, stable regions in an image. So you can, if you want, you can look up scale-based clustering in image processing. But that's still two dimensions, so there are a lot of applications. Okay, so with that, let us finish this topic and let us move on to another related topic. Right. Any questions on this so far? Okay, so let us look at another variation of this online clustering. So what we have begun with k-means clustering. We have then looked at an online version of k-means clustering, which we call computative learning. And from there, we took one direction and introduced this scale-based clustering. So now what we will do, we'll start with again on online or k-means clustering or online version of k-means clustering, which is computative learning, and look at a different model called the self-organizing map. So let us see what this is. So we have seen what is online clustering, right? You have this equation and we are familiar with that. We've also seen scale-based clustering, where clustering is done at a scale, right? So now in a self-organizing map, the clusters are, are given some IDs, and you arrange them as an index. So actually, let me kind of take a short detour here. And so the self-organizing maps are actually inspired by certain maps in the brain. So we call them brain maps. Okay, and it's a kind of a neural network model. So let me just quickly motivate this, where these kind of map ideas have come from. Oops, sorry. So that's not a very good. So let's say this is a picture of the brain, right? And so the surface of the brain is called the cortex. You might have heard it in your high school in anatomy or physiology. Now here there are certain parts of the brain which process sensory information. Like for example, when you are seeing something, right, the visual cortex, which is somewhere here, responds to visual inputs. Or when you're listening to sounds, the auditory cortex, which is somewhere here, responds to sounds. Or when you're touching something, right, or something touches you, or let's say a mosquito is biting at some point on your skin, right, that activates certain part of this region of the brain. So this is called the visual cortex. So this is called the auditory cortex. And this is called, the touch cortex is called the somatosensory. So this is the kind of sensation that comes from the body or soma. That's why it's called somatosensory cortex. Now, one thing about, it's easy to, so this kind, so what happens is different stimuli activate different neurons, right, in each of these regions. And it looks as if there is a map of that stimuli within these regions. Right, these are called topographic maps. Why are they called topographic maps? Let me explain. Take, for example, this somatosensory cortex. I'll just say SS. So this SS, if you look at the map, okay, let's say it looks like this. Now, the head part of your body surface is mapped here. So that is the head. Okay, I'm not a great artist, so please bear with me. Then this is the trunk, and hands go here, and fingers go here. Okay, and then legs. Actually, the foot part is very big. Similarly, the hand part is very big. Shoulder is small. Actually, the trunk is also quite small, but hand is very big. Okay, so it looks like this. So the whole body is mapped onto this little patch of the brain or set of neurons in such a way that if let us say somebody touches you on your forehead, neurons here will get activated. Somebody touches your thumb, neurons here will get activated. Somebody touches your toes, neurons here will get activated. So basically there is a map of the entire body surface in this small strip of the cortex. So head is here, toes are here, hands are here, and so on and so forth. And another thing about this, so one thing about this is nearby points on your body surface activate nearby neurons in this map. So there has two properties. So these are map properties. So nearby points on body surface activate nearby neurons. Right, so that's why it's called, first of all, a map. So because what is a map? A map is a representation of some outside, a place in the world, in such a way that nearby regions in that place, right, will get mapped onto nearby points in the map. That's why it's called a map. Similarly, here also the nearby points on the body surface activate nearby neurons in the map. And secondly, so parts of the body that present greater information to the brain are given larger representation in the map. So what does that mean? So if you look at the hands, right, the hands part of it, there are a lot of sensors, touch sensors inside the hands. So therefore, the hands are given a huge area in this map. Similarly, the feet, right, and the head region also has very rich distribution of sensors, especially the face part. So these regions have large representations. Whereas the trunk also, although it's physically very large, right, the trunk doesn't have too many receptors. In terms of receptor density is much smaller compared to, for example, your fingertips. Therefore, trunk area is actually quite small. It's given very small representation in this. So the amount of area in the map that represents a given part of the input, right, depends upon how much information is there in that part of the input space. Secondly, nearby points in the input are mapped onto nearby neurons, right, in this map. Okay, so how do you represent that here? So here in this artificial map, which is called the self-organizing map or SOM, self-organizing map, there are a set of neurons. It's a 2D array of neurons. Usually it is a square array. Sometimes it is not, but let us start with a simple example. And each neuron, so I'll call this neuron at location ij, and I'll call the output of this y. So y at ij is given by, you see the exponentials, the Gaussians keep showing up. And I'll imagine that there is a centroid sitting inside that neuron. But we have seen the same expression just a few minutes ago in the context of scale-based clustering. That same thing shows up here, but for a slightly different purpose. So at a neuron at ij, right, it gives a response is given by this. So what that means is, imagine that there is a centroid sitting there, and an input that you give from outside, that is x, okay, is given to all these guys. So you can kind of draw the map slightly differently like this. Okay, all these neurons sitting there, and each of them gets an input x. Input x goes to each of these fellows. And inside this, there is an MI. Imagine there is an MI here. And it produces an output. So it actually should be MIJ. Right? So output, so the MIJ, this is output YIJ. So earlier in the previous example, we just had a single index to the centroids because MI. Just some case centroids, and index is MI. But now it is not like that. I have n by n number of centroids. Okay, so and these centroids are also laid out in form of a grid for a special reason, because so this is how you construct this map-like structure which people found in the real brain. So therefore, for every Mij now there is a response which is Yij. Now, if you want to reproduce this map-like structure, what we want is, right, for a given x, right, I have a response at a given neuron, right, and let us say there is high response at a given neuron compared to all other systems. So that is like, so when we applied the nearest neighbor criterion in case of k-means clustering, we look at which is the nearest centroid. Now the same thing can be done slightly differently, because if a neuron is close to a given data point x, right, that means the corresponding Gaussian value will be high, right? So therefore, a nearest neighbor centroid, right, is same as saying a neuron which has the highest response. Okay, so if a centroid is closest to a given input vector x, it is same thing as saying that the corresponding neuron has the highest output Yij. So nearest neighbor, uh, so nearest neighbor concept now becomes neuron with highest response. That's like saying max Yij. So for a given input, the neuron with the highest response, this is what is called a winner. This is the terminology of a self-organizing map. Right? It's the same thing. So we have been deciding, how to move a given centroid, right? So in case of online clustering, how do you move a given centroid to a given data point? We'll move it only if it is the nearest centroid to the given data point. So here also what we do is we don't look for nearest centroid, we look for the neuron which has highest response, which is also the same thing. And we indicate that neuron as the winner. Now, so just like before, we move the winner towards the input. That means we do something like delta Mij is equal to some eta times x minus Mij. Okay, sorry, we do that just like before, but we do something more this time, because what we want is, right, in the previous thing, if you want it to work like a map, if a given neuron responds to a point on the body surface, right, nearby neurons in the also respond roughly to the same body surface, because it's a continuous mapping from the body to this map, right? So I cannot have, like, my little finger here mapped here, and my ring finger is mapped. If it is mapped somewhere here, that's bad, right? Because all the fingers of my hand should stay close to each other. So I cannot have little finger showing up here and my let's say thumb going here. That's not okay, because nearby points in the body surface should be mapped onto nearby points in the map. Okay, so to take care of that, we need to do one more thing, which is when we move a winner. So let us say I have This is my winner. Okay, so this is a winner, and I have some neighboring neurons. Okay, I'll just draw this a bit dark so that I can understand that it's a winner. So this fellow responds with the highest value to given x. Now what I want is even nearby neurons should respond to roughly the same stimuli. So if I make a small change in x, some nearby neuron should respond, because if this given value of x represents my little finger, a small change right in that x might represent my ring finger. Okay, so therefore a nearby neuron should respond to it. So how do I make this happen? For that, I need to define something called a neighborhood. Okay, so for a given neuron, I define a neighborhood, and when I update the given neuron by moving it towards a data point, I also update nearby neurons. So to define the idea of a nearby neuron, we define something called a neighborhood, which is given like this. If my map is a two-dimensional array, usually it's a squared array. Squared array is a standard thing. Then if I have a neuron like this, if this is my winner neuron, my neighborhood will be this 3 by 3 array just surrounding it. The neighborhood size can be anything, right? It can be 3 by 3, it can be 5 by 5. Generally, it is odd numbered because that's how you'll have an exact center. The winner will be the exact center of that array, or 7 by 7 and so on. I define a neighborhood. Sometimes people also take hexagonal grids. It should be a 2D array. People take hexagonal grids. So then again, the neighborhood looks like this. Okay, you have hexagons of increasing size. So so what we do in this algorithm is you not only move the winner, right, but also move. So this is a winner. So you can this ij index, when there's two indices, it's slightly cumbersome to use both indices all the time and use two subscripts. We'll just define one vector r. Okay, r represents that index vector. So then r star is I star and j star. This I'll call the winner, the winning neuron, which is the closest to the input vector. So if r this r star is my winner neuron, I take this bunch of other neurons. So move r star towards the input vector x, and also move r where r is in the neighborhood of the winner. So I'll call this, okay, so some special symbol which indicates neighborhood. Move that also towards x. Now, just like before, how do I make sure that only those which are within some neighborhood of r star are moved towards x, and how do I do that? For that, just like we use Gaussian in the scale-based clustering case, here also we use Gaussian or other functions. We use something called a neighborhood function, and that is given by this. This is like a capital lambda, uppercase lambda, which is a function of r star and r. So if r is very close to r star is a vector, like I star, j star. R is also a vector, index vector, right, I and j. If r is close to I star, j star, or r star, then this function will be big, otherwise it is small. So it should be decreasing with increasing distance between r and r star. So Gaussian is a good choice. Only thing is here, this Gaussian is computed not on the input space, it is computed on the index space. It is space of indices, this I and j. Okay, so finally what happens is I have an input vector x, right, and for that input vector x, I have a winner. So this fellow is the winner. And all these this outline, these squares that are drawn around it, they are the neighborhoods. Okay, capital N. Now, so just like in the case of online clustering, when I have a given input vector, so okay, people use this notation W instead of M. We use notation M in case of k-means clustering, but in case of self-organizing maps, people use notation M, but it's just change in notation. It means the same thing. So I have a input data point X or XP. P stands for pattern. Okay, P pattern. So find out which is the nearest centroid, which is WR star, and move WR star towards XP using this equation, which is just like your online cluster. So now for all other R, which are inside this neighborhood, okay, this special N, that which has all these neurons inside the square, update their centroids, right, which is WR, using this equation, which is only a small deviation from this equation. What's the difference between this and this? Equation 1, equation 2. In equation 2, we have this additional term, which is capital lambda RR star, which has a high value for R close to R star and low value for R far from R star. So this is called neighborhood function. So basically what is happening in this is, if a given centroid is close to my input data, X, right, I move this and not, so this is my R star. Let us say I have my another centroid R, which is far out. But in the array space, in the map space, this R is close to R star because it is inside this neighborhood. Then you move this fellow also close towards the same data point. Only thing is, the amplitude of this will be higher than this because this amplitude is suppressed by this neighborhood function. If R and R star are close to each other in the map space, then this amplitude is high, this capital lambda is high. But if R is far off from R star in the map space, this amplitude is small. So the neighborhood function looks like this. One is just a Gaussian, that is, it looks something like exponential minus of norm R minus R star whole square by some sigma square. It's just a Gaussian. There's one more function called a Mexican hat function. This is obtained by, for example, difference of two Gaussians. So, for example, if you take a Gaussian with high amplitude and small standard deviation, and another Gaussian with large standard deviation but small amplitude, and take a difference of these two, this is plus and this is minus, then the difference will look something like this. So this part will be minus and this part will be plus. Okay, so the same thing, if you rotate it in 2 dimensions, it looks like this. It looks like a Mexican hat, so therefore it's called the Mexican hat function. So you can use this or this, but this is good enough. Gaussian is good enough. Right now, how do you train this? How do you do this clustering? Right, using this map model. So when you run this algorithm over and over, right? So you just update these to present all the data, present data points one by one, and find the winner and train this, and then update all the centroids of the neighbors, and keep on doing it until the whole map settles down. Okay, and there's no more change. So here also people make sure that you use some kind of annealing. That is, in the early stage of training, you start with a large neighborhood size so that the whole map responds to your input data. Whereas with training, you reduce the neighborhood size. Similarly, even learning, right? In the early stage, you use a, this is your, right, and this is n. Okay, and initially start with large n and large eta and gradually reduce them as the training proceeds. So in this training or learning, there are two phases. One is called ordering phase, other is called settling phase. So let us see an example. So let us say I have data from a square. Okay, I'm not showing data here, but let us imagine that there is data that fills this entire square, unit square. So now I have a 2D map. I want to train using just data drawn from a square. And initially, I initialize all the this Wijs or your right, this centroids of all the neurons, right, randomly, so that they are all very close to the center of this square. So all the centroids are close to initially close to half and half. So they're all close to the center. So now you present data points one by one, see which one is closest to it, and move that weight vector towards it, and move the weight vectors of all the neurons within its neighborhood, and keep on moving and develop the map. So you see that map is expanding now slowly. From initially, it's all as though it's all crumpled and concentrated in the center of the square. But as training proceeds, the map starts kind of unfolding and starts expanding. And so this unfolding has reached a certain stage. You can now see that the map is also like a square grid, right? And after this, it will expand further, and finally, it will fill the entire square. Because so this is just a pictorial representation. What it says is, so basically in this map, at each of these intersections, you imagine that there is a neuron, or there's a weight vector, or your centroid, right? And so that centroid responds to points around this region inside the square. That's what it means. So by the way, it has taken about 1 lakh iterations, right, to reach this point. So you see that in this process of unfolding, there are two stages. So initially the map, if you look at this stage, it's all crumpled. That means a neuron which is supposed to go to maybe this region of the map is in the opposite region, and so on. So there's a lot of twists inside the map. And as the map is trained, as you keep on presenting data as map is trained, all these twists and kinks will get sorted out and will get cleaned out. And you see that most of the kinks are cleared at this point, right? And once you see that in this picture, right, all the kinks are gone. The array now looks like a square grid roughly, but only thing it's a bit distorted. Okay, and after this, now it's pretty much a square grid. After this, only expansion. There are no more folds and kinks in the map. So during map training, you see there are two phases. In the first phase, all these kinks are removed, and map gets ordered. What is called ordered? This phase is called the ordering phase. And in the second phase, once ordering is done, then there's only expansion of the map to fill the entire input space or the entire data set, and that is called the settling phase. So at the end of it, all the centroids of the map stop moving. They don't move anymore. You can keep on presenting data, but they have reached their equilibrium state. Okay, so after that, there is no more change. So just one more example. So in this case, the data set has not a single square, but 4 small squares. And the map happens to be a 1D map, right? That means the neurons are arranged as a 1D array. The examples that we have seen before are all 2D maps. So, but if you have a 1D map, then your neighborhood is also a 1D neighborhood. So if I move a given neuron towards a given data point, I have to move only its immediate neighborhood on this linear map, on this 1D map, towards the input data point. Your neighborhood is also 1D in this case. When you do that, you apply this 2D data set to a 1D map, you see how the map is organized itself. So one bunch of neurons, so see that map is a chain. Okay, so it starts in this top right square and ends in the bottom left square. So most of the neurons are concentrated in the data point, the places where there is data, and out there in the right in the middle of nowhere, where there is no data, you don't have many neurons, right? There are not many cluster centers, right? Out there where there is no data, which is good, which is what we want to have. Okay, so another interesting property of a map is that if you, as the map unfolds, right, uh, it starts resembling something called as space filling curve. These are sometimes also called Peano's curves after the person who kind of worked on them, mathematician who worked on them. That is, if you let us say you take a data set which is inside a triangle and you expand the map, after some point you see a shape like this, and after some point, so you see that this kind of a angular region expands into another structure which has three kind of branches in it. And if you expand this further, each of these things again, so you see that this projection is now expanding into something which has three branches. Okay, initially we had just this one. This expanded into something which has again three branches. Okay, so every part of it, every one of these projections expands out into something which has three projections, right? So the curve that you get in the process will have the property of self-similarity. Okay, such self-similar curves are studied in a branch of mathematics called fractals. It's very interesting that the self-organizing map model, which has nothing to do with originally fractals, when you actually train it on simple 2D data like this, you take 1D map and train it on 2D data, you end up with such self-similar curves which are encountered in the topic of fractals. Okay, so let us stop there and let us continue in the next class. We'll look at some applications of a self-organizing map in biology. Okay, any questions? Questions? No questions? Okay, so talk to you tomorrow. See you.